Hello everyone, this is Athreya and welcome to our channel CodeChef. Today we're going to be solving the problem Life Limited with the code of LIFELTD and the difficulty level of simple. Let's get started. Here it's written that we are supposed to test the logo of a company that they have created. A logo is a 3x3 square with 9 cells. For example, this is our format where we have 9 cells in the form of a 3x3 grid. 3 cells in the first row, second row and third row. So 9 cells in total. Each cell contains some lowercase English letter. So any of these cells can contain a lowercase English letter. The logo is considered to be good if there exist 3 cells in the shape of a capital L that contain the letter lowercase l in each of them. For example, this is a valid logo because it satisfies the property that you have the design of an L using lowercase l's in the cell. This will be clear if you read the below statement. That is, for every cell that if there is a cell that contains this lowercase l here, for example, this is a lowercase l here, then the cell directly beneath it should also have an L. So the cell directly beneath this cell should also have an L. So far so good. And the cell to the right of the second cell should also have an L. So this cell is to the right of this cell and this also contains an L. Hence this is a valid logo. So as long as we can find at least one group of 3 cells satisfying this property, where if you have an L here, the below cell has an L and the right cell has an L, we are good. The logo is good. For example, let's say another example. Let's say this example also is a valid logo because here you have an L, the cell directly beneath it also has an L, and the cell to the right also has an L. So this is the example of a valid logo again because this satisfies the property given to us. However, if you want an example of an invalid logo, this is an example of an invalid logo. For example, let's just say A, B, C, D, F, F. This is a random grid here and this is an invalid example because we have 3 L's here and these L's do not follow the property, because our logo will be good as long as we can find at least one pattern of L. So this pattern of L is characterized by one group of 3 cells, where if you have an L, the cell beneath it will also have an L and the cell to the right of that will also have an L. So as long as we can find at least one L pattern, we are good. We can have many L patterns also, as we'll see in the sample cases, but the sufficient condition is finding one pattern like this. Then the logo is good. However, if you find no such pattern like this, the pattern is not good. Or you can say the pattern is bad or no is the output. In this case, again, the pattern is there. So this is also a good logo. Let's look at the sample cases. This is the number of test cases and there are 3 test cases given to us. This is the first test case. This is the second test case and this is the third test case. If we look at the first test case that is given to us LAZ and all this, we can easily see that there is a pattern. If you look at this first cell here, this contains an L, the cell beneath it contains an L, and the cell to the right of that contains an L. So immediately you found a pattern using lowercase L's, a pattern of L. Immediately once you find this pattern here, you can just break out and say that the answer will be yes for this particular test case. Let's look at the second test case. Even though you have a group of 3 L's here, it's very important to note that this is not the required pattern, because what pattern we are looking for is, if there is an L, there should be a L directly below it and there should be an L to the right of it. This is the pattern that we're looking for. We are not looking for a pattern where you have an L to the left. Here, if you have an L here, this is not a valid pattern. Only this is the valid pattern here. So this is not good logo, or the output should be no, because we don't have any group of 3 cells following this strict pattern where you have an L, the below cell is L and the right cell also should be L. You can say that, hey, this is L and the cell below it is L, but you don't have the third condition. Instead of A here, if we had an L, it would be a valid logo. Now here we have many valid logos. For example, if you take this particular logo here, you have an L here, the cell below it is L, the cell right of it is L. This is a valid logo. For example, if you want to take from the starting cell here, this one, this is an L, the cell below it is an L, and this is also an L. This is again a valid logo. Since there are many such valid logos, the output will be yes, because the sufficient condition is just one such logo like this. If you have an L pattern here, you have a multiple L patterns like this, it's all the more good. But the sufficient condition for us is if we have at least one pattern like this. As soon as we find one pattern like this, for example, if we start from the first cell, this is an L, the cell below it is an L, and the cell to the right of it is an L. As long as we find one pattern like this, we can immediately break out and say that the output should be yes. Let's look at the approach. We look at two approaches to solve this problem. The first approach is a straightforward approach. If we consider the cell ij, let's say that we are at the cell ij in this particular matrix and we want to figure out whether whether there is a pattern of L's here. We know that for the patterns of L to be good, we know that for if this is an L, let's say that ij, you are processing the grid row major wise, you are processing row by row, and you are currently at the cell I comma j, and this is the I comma j you are currently at, and this is equal to L. You found an L here. In order to find a pattern of L from starting from this cell ij, it is sufficient to have the cell directly beneath it to be an L and the cell to the right of it to be an L. So what will be in terms of cell notation? If this is ij, the cell directly beneath it will be I plus 1 comma j. If the cell ij equal to L and the cell I plus 1 j equal to L and the cell I plus 1 j plus 1 equal to L, we have reached our sufficient condition, and if these three are satisfied, we have found our pattern of L. In this case, this is ij, this is I plus 1 comma j directly beneath it, and to the right of it we have I plus 1 j plus 1. Since these three are L's, we have found our patterns of L's, and we can immediately break out if we find such pattern, and we can end the program there itself. Because we process row major wise, let's say that we process row by cell by cell basically. We process this cell, this cell, this cell, this cell. We process cell by cell and we check if this pattern is satisfied in any of those cells. So while we are processing cell by cell, what we're exactly checking is from that particular cell, is there a pattern of L possible? So for every particular valid cell, we look at the cell directly beneath it and we look at the cell to the right of it if this pattern is satisfied. Now this is one approach. The second approach is kind of a different approach where we try to flatten the 9 cells. We know that all the the input given to us is always a set of 9 cells. This approach one will work for any n into n grid. If we just look at this pattern, even though in this problem it is specifically given to us that we only have 3 into 3 grids here, but the second approach makes use of the fact that we are only given 9 cells. For example, if we try to flatten the grid, for example, this particular case XLX, XLL, XXX, instead of taking this as a proper matrix, what if we flatten it into a 1D array like this? So what I've done is nothing but this XLX is the first row, this XLL is the second row, this XXX is the third row. I've done nothing but written the grid here in the 1D array format. Now, if this is my ij I'm currently processing, let me write in 0 indexing form. 0, 1, 2, 3, 4, 5, 6, 7, 8. So in this particular case, because there are 9 cells, it corresponds to the indices 0 to 8. Since I started from index 0, I stop at index 8. Of course, you can use 1 indexing and have it from 1 to 9 also, but I'm just using 0 indexing so that's simpler. Now, if I'm currently, if I encounter this L here in my 1D array, is it sufficient to check plus 3 and plus 4? Why I'm saying plus 3 and plus 4 is that, let's say I'm flattening my grid as I did right here. So instead of checking for I plus 1 into j, which I was doing previously, it is sufficient to check plus 3 here. Why plus 3? Because if I flatten my whole grid here, this x is one distance away. This is one distance away. This x is two distance away from L. Because if I write x, L, x, x, this first x is this green x here, that is distance of 1 away from L. This x here is this x here, which is distance of 2 away from L. This L here is a distance of 3. Distance of 3 from this particular L index, and this second L, third L here is actually a distance of plus 4 from my particular L here. So what I'm trying to say is you can also approach this by flattening in the form of a 1D array. Since the pattern of L is a group of 3 cells that follows this property, when we flatten it, we can use a property that if we have an L here at a distance of 3, we have another L here, and at a distance of 4, that is 1, 2, 3, 4. At a distance of 4, we have another L here. So from this L plus 3 and plus 4, we have L and L. We know that we find a valid pattern. But it is very important to not fall into the common mistake of not trying out corner cases and just assuming that this second approach will work. Because the second approach is not like the proper brute force approach where we are checking from every cell down and right exactly. It's kind of a little modification to that. So let's take an example like this. I have XXL, XXL and LXX. So basically, if we look at this, we know that there are no pattern of three cells that follow, our required L pattern. If you have an L, below it should be an L, right it should be an L. There is no such L here. But when I flatten this, let's say I flatten this. What happens if I flatten this into a 1D array? I get XXL, XXL, LXX. Let me write the indices 0, 1, 2, 3, 4, 5, 6, 7, 8. According to my second approach, what we are going to do is we are going to check each of these indices. If you have an L, if there is an L, you're going to check that index plus 3, that index plus 4 and check if those are also L's. Now I found my L here. This is index 2. 2 plus 3 equal to 5. I found another L here at plus 3 index and I found another L at plus 4 index. Since I found corresponding to my index L, I found at the plus 3 location and plus 4 location L's, I will immediately say yes, the logo is found. But is that really found here? In this case, there is no logo found following this pattern. So we found an essential corner case to our solution, that this solution will not work in this particular case. So what will we do to avoid this? So that's why in order to make approach 2 work, approach 1 you don't have to do anything. You're just going to process each cell and check this and it'll work out. But for approach 1, first we need to understand that the potential L's can be formed starting from which indices. For example, starting from index, let's assume that I'm starting from 0 based indexing. This is 0, 0, this is 0, 1, this is 0, 2, this is 1, 0, this is 1, 1, this is 1, 2, this is 2, 0, 2, 1, 2, 2. So I'm using 0 based indexing here where the starting cell is 0, 0. So here, starting from 0, 0, can I get an L? Yes, if my 0, 0 is L, if my 1, 0 is L and my 1, 1 cell is L, there is a potential of an L formed starting from index 0, 0. This is a potential starting point for my L. Starting from index 0, 1, can there be a potential L? Yes, if 0, 1 equal to L, if my 1, 1 equal to L and my 1, 2 equal to L, there is a potential of an L that is formed starting from my index 0, 1. This is a potential starting point. Now from my 1, 0, can I form a potential L? From 1, 0, there is a potential of forming an L where the starting is at 1, 0. If 1, 0 is L, if 2, 0 is L, and if 2, 1 equal to L. This is a potential starting point. From 1, 1 if I start and it's L, and 2, 1 is L, and 2, 2 equal to L, there is a potential of a starting point starting from 1, 1. So is there any other potential starting point for my L to be formed? For example, from 0, 2, even if I have an L here and I have an L below at 1, 2, there is nothing here. This is out of bounds for my 3 into 3 cell. So this is not a valid starting point. I'm just coloring this so that you know it's not a valid starting point. Now, is my 1, 2 a valid starting point here? If I start from 1, 2 L and I have an L here, is there any possibility of forming an L here? No, because this third cell is out of bounds. So my 1, 2 is not a valid starting point for my potential L. Now, no matter if 2, 0 is L, there is nothing below 2, 0 and there's nothing to the right here because that will go to my fourth row here. I have my first row, second row, third row. I have no fourth row. Similarly, I have no fourth column here. So I can just essentially not process my third row itself. Because what is the use of processing my third row here? Because I know that there can never be the possibility of a potential L starting from my third row elements. Because if 2, 0 in 0 based indexing, my 2, 0 equal to L, below 2, 0 there is nothing. Below 2, 1 there is nothing. Below 2, 2 there is nothing. So even though 2, 0, 2, 1, 2, 2 may have an L, there is no potential L pattern that can be formed because below this there is nothing here. So I can just ignore all of these cells. So it is sufficient to process these 4 indices here in my approach 2 and check if there is an L that can be formed, because the main thing that we have here, only 9 cells. Only 9 cells what we have here given, 3 into 3. So here it is sufficient to check these 4 indices, what I am not colored, basically 0, 0, 0, 1, 1, 0, 1, 1. But now since we are flattening the grid like this, so 0, 0 is nothing but index 0 because the first element will also be at the starting here. Now my 0, 1 will be at the index 1 here. And my 1 comma 0, what will be? If I have, this is index 0, this is index 1 after I flatten, this is index 2, 1 comma 0 is index 3 after I flatten, index 3, and 1 comma 1 will be nothing but index 4. So because this is 0, 1, 2, 3, 4, 5, 6, 7, 8, right? That's how we flattened it. So it is sufficient to check the indices in my flattened 1D array, the indices 0, 1, 3 and 4, because they are the only potential starting points for my L. So I will check, I will use the same approach, plus 3 and plus 4 from the required index if the current index equal to L, but I'll check it only for indices 0, 1, 3 and 4. So if these are satisfied, I will say that yes, if any one of these is satisfied, that means if, from 0, if this is L, if this is L, and if this is L, it means that I have my potential L starting from 0. If my 0th cell is L and my 3rd cell is L and my 4th cell is L, plus 3 and plus 4 condition, if I have 3 cells, or I have a potential L here, so I break out and say yes. So this was the other approach. That's why this was very important to not just jump into this plus 3 plus 4 approach, because looking at the corner cases that can fail this approach. So this is one of the common mistakes where you always have to try out corner cases instead of just believing that your approach is correct and then rectify those corner cases. Now since we rectified this particular corner case of our solution and we're only checking from these cells, and our condition is that there are only 9 cells given to us in each of the test cases, this approach 2 will work properly. Approach 1 was more of a straightforward general purpose approach that would work for any n into n cells, because you just had to process cell by cell in a row major order, and you're actually checking the ij. If it's L, you're checking I plus 1 comma j, and you're checking I plus 1 j plus 1. So you're checking the proper way throughout the matrix, and this was the approach 1. So the other common mistake was you always have to check for out of bounds condition. For example, if you just, for example, without checking for out of bounds, if you have a loop like 1 to 3, and you have a loop from j's 1 to 3, and you're checking j plus 1, for example, and you have a matrix that you ingested that was 3 3 size. Now since this j plus 1 is always now since there is no j plus 1 here and j plus 1 equal to 4, this will run into out of bounds, because your array was only from 3 to 3 or from 4 to 4 if you follow 1 indexing. This in case you follow 0 indexing, this in case you follow 1 indexing. So if you follow 1 indexing, for example, and you had defined a matrix like matrix of 4 comma 4, for example, this, and you are using the indices from, let's say, 1 to 3 and 1 to 3, these are your valid indices. But then when your j plus 1 becomes 4 here, it runs into an out of bounds condition. So you have to check in if you're using j plus 1 or you're using somewhere I minus 1 or something. It is essential to check that you're not running to out of bounds. That is, you're not processing any index that is less than 0 or less than 1 based on your implementation, or you're not processing any index that is greater than the maximum range of your indices. Now let's look at the code for the approach that we have just discussed. First, we will look at the approach 2 here. That involves flattening the matrix given to us. We know that we are always given 3 into 3 grids. So if we flatten the grid, we will have indices from 0 till n into n minus 1. So if we have 3 into 3 grid and we flatten the 9 cells into a 1D array, we will have the indices from 0 to 8. So I'm having a concat string here, and for in range 3, I'm appending it to my string here. Basically what I'm doing is I'm flattening the grid here. For example, if I have my matrix as A, B, C, and let's say XLL, okay, XLL, and I have, let's say, LLL again. So if I flatten this, I should get ABC, XLL and LLL in a single string here. So in order to do this, what I'm doing is for underscore in range 3 here, because n is 3 here. So I'm processing row by row and I'm appending it to my concat string. So in the first iteration, my concat string will be ABC. The second iteration, my concat string will be ABC XLL. The third iteration, my concat string will be ABC XLL LLL. It's totally like this. Now after that, I'm processing index by index of my concat string, but I'm only checking those indices that have the potential of an L being formed, with that index being the starting point. So we found out that the indices 0, 0, 0, 1. For example, we found out 4 potential indices. Only for those potential indices, I'm checking if that index equal to L, that index plus 3 equal to L, and that index plus 4 equal to L, and I'm printing yes. Now this is very, normally in C++ to do this, you would have a Boolean boolean variable where you set this to true, and then you check this outside the for loop. But Python is very handy in the case that you can pair an else statement with the for loop itself, so no need of an extra boolean variable. We can just print yes and break if we find it. Otherwise, in the else condition, no will be executed, which is exactly what we want. So hope this part is clear of the approach 2. Now the approach 1 is very simple, and that is the C++ code here, where we're inputting the matrix here and we're using one indexing here. So we are inputting the matrix in this block of code, and after we input the matrix, we use a boolean variable like discussed. Now this boolean variable will tell us whether we have found out at least one pattern of an L. Now we know that it is useless to process the third row. As we saw, if we process the third row, there is nothing below the third row, so none of the cells in the third row have the potential of being a starting point of an L pattern. So we can ignore the third row. It is sufficient to process row 1 and row 2. Then we process j equal to 1 to 3. So if the current cell what I'm looking at is an L, I am supposed to look at the cell immediately below it, which is I plus 1 j, and the cell to the right, that is matrix I plus 1 j plus 1. If these three cells are L, I have found a pattern, and immediately after finding a pattern, I break out. Now you might ask that why are you checking here j plus 1 and not checking for I, even though you're using I plus 1. Because I am restricting my outer loop I to go only to the second row, there is never a case where I plus 1 will be out of bounds. However, since my j is going from 1 to 3, there is a potential of my j reaching an out of bound condition. That's why I'm checking this here, just to be sure. Now, if my boolean variable found equal to true, I'm outputting yes. Otherwise, I'm printing the output as no. So hope this is clear. Hey guys, that was it. Thank you so much for watching this video, and if you haven't yet done this, this is a gentle reminder to hit that subscribe button. If you're interested in competitive programming and data structures, this channel is a one-stop solution for you. See you in the next video. Bye.